Hello students, welcome back to Organic Canvas. In this video, I'm going to teach you how to predict the products for the ring opening reactions. Students, don't get confused this with ring expansion. In case of ring expansion, we convert 3 to 4 or 4 to 5 or 5 to 6 membered cyclic molecules. That means what? Here the reactant and the products are going to be cyclic molecules. But in case of ring opening reactions, you are converting the cyclic molecule to a cyclic molecule or open chain compound. So how to predict products in such reactions, that's what we are going to learn. So the given molecule is an epoxide molecule wherein we are having a carboxylic acid group as well. When this epoxide is heated, there is no reagent, there is no catalyst, then how to predict this reaction? Many students cannot predict the first step itself. They get stuck here, therefore they cannot solve the questions. Don't worry, I'm going to give you a simple trick how to solve such questions. First, identify the functional group. Look at this. This is ether. Ether, oxygen is having two lone pairs of electron. That means what? This is electron rich. Hence, it's going to act as a nucleophile. Now, is there any other reactive center? Is there any other reactive center here? Carboxylic acid. And you know that acids are proton donors. So that would be the first step. The carboxylic acid will give away the proton so that the formed carboxylate ion will be stabilized by resonance like this. What about the phenyl groups? They remain as it is. Then what about the lone pair of electrons? So one of the lone pairs, it's going to donate to the incoming proton like this, right? Therefore, it's going to form a positive charge here. So oxygen is trivalent. Can it be stable? No, it cannot be stable. So what it does, it will break this bond. So whatever the polar bond is there here, it will break and oxygen will take the electrons. Look at this carbon. I'm talking about this carbon is attached to two phenyl groups. Write down that as it is. When it takes the electrons, it will become plus. And what about here? We have an alcohol and of course there is a hydrogen and it is attached to carboxylate. So now what happens? This carboxylate cannot be stable because we are heating this, right? Since we are heating, it will undergo decarboxylation. What is the driving force for the decarboxylation? When it undergo decarboxylation, the bonding electrons will shift here to stabilize the formed carbocation. Why this carbocation was formed in the first place? Because of the phenyls. Both the phenyls are going to stabilize the formed carbocation. Hence, it is formed in the process. Now, it is being stabilized by the bonding electrons here like this, right? And then what do we have here? We have OH and H like this. Now, what is this? This is enol. Can enols be stable? No, enols will always undergo tautomerization. So, tautomerization is always could be in dynamic equilibrium. So, how can you write this? Look at this. So, this is aldehyde. Therefore, you can call this as aldo-enol tautomerization. So, what will be the product now? The aldehyde is the final product. Check the options. Where do we have aldehyde? So this is acid, not possible. This is a lactone, that a four-membered ring, so not stable, right? What about this one? This is the exact product what we got here. So this is the correct answer, not even option D. Students, this reaction when you observe, the reactant is an epoxide. The final product is an aldehyde. So epoxide to aldehyde, generally if we do it in presence of a catalyst, right? So this is a named reaction called as Meinwald reaction. But there generally we use a catalyst. But ultimately you are going to convert epoxide to aldehyde. But here since we are using carboxylic acid, so it is acting as catalyst within the molecule, right? So it's similar to the Meinwald reaction, which is a named reaction and it's very important for JEE Advanced exam. Let's understand one more ring opening reaction. So again, we have a cyclic ether, which is 5-membered and it is treated with concentrated H2SO4 and heating condition. What could be the product? Remember, the concentrated H2SO4 generally acts as a catalyst and we also call it as a dehydrating reagent. So it can dehydrate. it can remove water molecule from such reactant molecule. So how it happens in this case? For that, you should know how to predict the mechanism of the reaction. So as I told you earlier, always protonate this oxygen. It will help you to understand how you can write the next step. Now you can see that we have a tertiary carbon here, right? So tertiary carbocations are quite stable. So you can break either this bond or this bond so that you're going to generate a carbocation here. How about here? CH2, CH2, carbon attached to two methyl groups, and here we have OH. Now, how can you stabilize this carbocation? By removing this proton, right? Because ultimately you have to get a stable product, right? So the carbocation is already tertiary. So just stabilize it by writing a double bond. Now what do we have here? We have CH2, which is in turn attached to methyl, methyl and OH. Now, although this is stable, still you have acidic medium, right? What happens? Tertiary alcohols are pretty reactive, right? So here again you are going to get oxygen, which is positive charge. So will it be stable? No, it will again undergo dehydration. How does that happen? Via the formation of the carbocation. So you can call this as E1 elimination because you can see there is a carbocation formed in the reaction. So ultimately you are doing dehydration and you are getting conjugated double bonds like this. And check for the options, where do we have it? So definitely we are not going to get phenol, so it has to be option B. Why not C? See, we are supposed to have some oxidizing reagents. Only then we get products like aldehydes, ketones, etc. Right? Here we cannot simply oxidize just by using sulfuric acid. Same here also. So you can eliminate options C and D. So the correct answer is as shown in option B. Let's solve one more ring opening reaction. So you might have observed so far we have used cyclic ethers only because they are the one which are not so stable and they can open up ring in presence of a catalyst like an acid. So here we have a 6-membered ring, right? And we have a 3-membered ring. So obviously we will open up the 3-membered ring. So when it is treated with an acid, just attack this proton with the help of lone pair of electrons present on the oxygen like this, and you are going to get a carbocation. Now what happens? This is not stable. It will take one of the bonding electrons, the pair of the bonding electrons, and say if the bond is breaking here, the carbocation will be formed over here and we got OH. And the driving force here is aromaticity. If this molecule forms a double bond over here like this, then it's going to be aromatic in nature. Nothing but here it is a phenol molecule. So we know that phenol molecules are aromatic due to the cyclic planar. There is a continuous conjugation and it will obey Huckel's 4n plus 2 pi electron rule as well. So that is the driving force to open up this epoxide to form the product as shown in option A. Therefore, the correct option is A. Students, here I have taken two reactions to explain how epoxides will open up in acidic medium and in basic medium, because the products what we obtain in these two conditions are entirely different, and this is specific for unsymmetrical ethers. Why this is unsymmetrical ether? Because you see this carbon is attached to two methyl groups and this carbon is attached to only one methyl group. So in this case, how the ring, that is nothing but epoxide ring, will open up to form two different products. Now, in presence of an acidic medium, what will be the first step? The first step will be the attack of proton on the lone pair of electrons present on the oxygen, because since proton is an electrophile and oxygen is having lone pair, it will donate its lone pair to the proton, and then we are going to get a reaction intermediate like this. This reaction intermediate is not stable as oxygen is having positive charge and it is trivalent. Now it has to break the bond either here or here to open up the ring. How it does? Whenever we have a carbon with 3 carbons attached to it, nothing but a tertiary carbon, right? Then the bond prefers to break here. Why so? Because the resultant reaction intermediate is going to be a tertiary carbocation. Look at this carbon is attached to 2-methyl, and then this carbon in turn attached to methyl and OH. So oxygen got back its lone pair of electrons. Since a cation, right, so the overall reaction intermediate is rearranged to a tertiary carbocation, which is quite stable. Then what happens? The methanol, which is a nucleophile. Why is it a nucleophile? Because of the lone pair of electrons present on the oxygen. It is going to attack our carbocation. Look at this. This OH will remain as it is. So this oxygen is attached to methyl and hydrogen. But what should be the charge now? It should be positive on the oxygen, because a positively charged molecule reacting with a neutral means the resultant will also be a positively charged intermediate. Now we have to regenerate the catalyst. So how do we regenerate? This hydrogen will leave as a proton by giving away the electrons to oxygen. We are going to get an ether, and look at its structure. This is exactly what is written over here. So you see the carbon is attached to the OMe, right? So this is nothing but a secondary alcohol. So here the methoxide is attacking, right, ultimately at the carbon where there is more substitution. So this is how you can remember. And why it happens so? Because of the stability of the tertiary carbocation. Now, what happens in case of basic medium? So when we take this methoxide or sodium methoxide, there won't be any reaction intermediate as a carbocation. So when we take this unsymmetrical ether with sodium methoxide, it will open up the ring when the nucleophile attacks the electrophilic carbon, or where there is less steric hindrance, because this is also electron rich, this is also electron rich, right? Since oxygen is electron rich here, this carbon is slightly electrophilic, so is this carbon. Now the question is whether it will attack here or it will attack here. It prefers to attack from less substituted end, or you can call it as less sterically hindered side. Therefore, it will attack on this carbon so that it will open up over here. So based on the arrows I have used, look at this will become O minus, right? And what about here? OCH3, like this. A neutral molecule reacting with the negative means the resultant reaction intermediate or the product is also negatively charged. So at the end, you can see that when we add some water to this, the alkoxide will become alcohol. And look at the structure of the product formed here. You see the methoxide attack where there is a less sterically hindered side, and here we are getting a tertiary alcohol. Here we are getting secondary alcohol. Here it is a tertiary alcohol. So that means what? We are getting two different products which happens to be isomers. How do we know what kind of products will be formed? So based on the reaction condition. So using this much information, let's solve a question based on this. Now let's solve a question based on the ring opening of epoxide molecule in basic medium. Here the stereochemistry of the reaction is important, as well as the options given have different stereochemistry. How to approach this question? First, look at the reaction medium. So this is basic medium. And what about the epoxide? You can see that this ring is above the plane and methyl is below the plane. And where do we have steric hindrance? The steric hindrance is at the first carbon but not at the second carbon. Why so? Because there will be hydrogen here which is below the plane. Now, whenever we do this reaction in basic medium, the nucleophile here is OH minus. First, you need to decide where it will attack, first carbon or second carbon. For this, remember, steric hindrance plays a very important role. It attacks from the side where there is less steric hindrance. The less steric hindrance is this side. So, OH should attack from here. Now, should it attack from above the plane or below the plane? This is called as stereochemistry of the reaction. So for that, remember the oxygen having lone pair which is above the plane is already electron rich. The hydroxide which is attacking, that is also electron rich. So it attacks from the side of opposite of the epoxide. So here it is above the plane, means the OH minus will attack the second carbon, and that too from below the plane. So at second carbon, OH should be below the plane. So you can see that A and C both have that option. But where this oxygen will go when the bond is broken, since it is above the plane, it will remain above the plane. So how to write the product here? Methyl is below the plane, write that as it is. The oxygen is above the plane, that also will remain as it is because the reaction is happening at this carbon, not at this carbon. So the stereochemistry will remain as it is on this particular carbon. But since OH is attacking from below the plane, right? So it is below the plane. And what happens to the hydrogen? It is forced to go above the plane. So here it is like this. Now, check for this particular product. We need to have OH above the plane, methyl below the plane, and OH below the plane. If hydrogen is not given, it's understood that it is above the plane, because when two bonds are in the plane, one is below the plane means the other one will be above the plane. Therefore, the correct answer is option A. Why not C? Because you see the stereochemistry of OH and methyl, it's been exchanged. So this is not correct. Hence, the final answer is option A. Students, in order to check your knowledge regarding ring opening reaction, you can always solve more and more examples. However, I have given one question at the end of this video, so please do solve it and comment your answer to know the key. Thank you.